Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. ESIG is the lead on Pillar 1, and more information on the G-PST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the November monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we use the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG15 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar is going to cover the Irish journey to 75% non-synchronous renewable generation levels. This is a fascinating story, which I have had the privilege to observe from close up over the last 10 years, working with both EirGrid and SONI. It is a journey which many other system operators are in the middle of, with the increasing shares of wind and solar power and batteries being added to their systems. Today's webinar will feature Simon Tweed, who is with EirGrid's Innovation and Planning Department. He's leading the development of the future operational solutions that will enable Ireland to achieve its very ambitious renewable energy targets. Simon was previously the lead engineer overseeing the day-to-day operation of EirGrid's National Control Center, so he speaks with a voice of experience. I'm very pleased to have EirGrid as a member of ESIG and to have Simon here with us today. Over a decade ago, the 2 TSOs on the island of Ireland, EirGrid and SONI, started on a journey to transform the operation of the island power system to be able to integrate non-synchronous renewable generation, mainly from wind. Today, they operate the power system with up to 75% instantaneous penetration. Tomorrow, who knows? Today's webinar will provide an overview of this journey, starting with the identification of the power system challenges and going all the way through to the technical and market solutions developed to overcome them. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG15 to ask your questions. And without any further ado, let's go ahead and get started. Simon, I will now turn it over to you.
Okay, thank you very much, Charlie, and good evening from Dublin. So I think Charlie has introduced the presentation very well, So I think we'll just kind of get straight into it. First, maybe just to set the scene a bit and provide a bit of background on who we are. So SONI and EirGrid are the TSOs in Northern Ireland and Ireland respectively. So SONI is the system operator of Northern Ireland in the north, and EirGrid is the TSO in the south. As you know, Ireland is an island on the western edge of Europe, and I suppose our geography probably informs quite a bit of this journey. So we are an island system and a single synchronous area. And we're also facing onto the Atlantic Ocean, and this provides a fantastic wind resource for us that we're kind of beginning to use to meet our electricity needs into the future. So maybe to set the scene a bit more on what this presentation is about, really it's about our story about the integration of wind into the electricity system, and as per the title, up to 75% of our instantaneous demand on the power system being met by wind. So this was the graph here illustrates a snapshot of a day. This was actually last Friday. It's quite a windy day here in Ireland. So you can see that wind made up a huge proportion of our demand for much of the day. So overnight, the morning load rise through the afternoon, and then probably bad timing from from the control engineers working in the control room point of view, but the wind then reducing quite dramatically as we come up to our evening peak. So we're a winter peaking, evening peaking system around 6 p.m. in the evening, up to about nearly 6 gigawatts of demand. And at that time, the wind front was passing over the country, and wind was dropping from about 4,000 megawatts down to under 1,000 megawatts at our evening peak. So I suppose what this kind of demonstrates is some of both the benefits in having lots of wind on the system, helping to meet our demand, but also some of the challenges that it brings, both in operating very close to the demand, but also when we transition from a windy period to a less windy period. And we hope that in what I'm going to set out over the next couple of slides, that our experiences in being able to accommodate kind of these type of conditions on the system can be of benefit to other power systems. So this is a bit of a look back at the past decade or so of the work that EirGrid and SONI have done to get to this place where we are today. So the structure of the presentation, I have just a couple of slides just to provide a bit more background on our power system. I then get into the meat of the presentation, which is the journey to 75% and some of the operational, the market, the tools aspect of things that the challenges we had and the solutions we developed to get to where we are today. And I'll finish with just a brief look at what's beyond this 75%. So this is an overview of the transmission system in Ireland and Northern Ireland. So as I mentioned, we're an island power system, a single synchronous area. Our transmission system extends from 110 kV up to 400 kV. We are operating across the two jurisdictions of Northern Ireland and Ireland. So there's two TSOs operating together, but it is a single synchronous area. So we're AC connected between north and south. But we have HVDC interconnection to our neighbours in Great Britain. So there's two approximately plus or minus 500 megawatt HVDC interconnectors from both from the north and the south to Great Britain. So our peak demand is close to 7 gigawatts. We're a winter peaking system. Minimum is about a third of that in the summer. Types of demand, we don't have that much heavy industry left in Ireland. But a lot of new global sort of tech firms, chip manufacturing, also pharma companies. So a lot of, I suppose, sensitive and demanding customers connected to the system. So, security and quality of supply is very important to them. On the generation side, I suppose the big part of this story is the amount of wind we've installed. So nearly 6 gigawatts of wind, which is obviously a significant proportion of our peak demand. We've seen peak wind of 4.5 gigawatts. That was the peak last year. It continues to grow every year. In terms of other renewable sources, we really only have a small amount of hydro, maybe 100, maybe a couple of hundred megawatts of hydro on the system. We don't have any nuclear on the system. We have, I suppose the balance of where we get our generation from is mostly from gas, coal and oil generators dotted around the system. And really we don't have much in the way of indigenous fossil fuel supplies. We have some offshore gas, but really the vast majority of the fossil fuels we're burning in those stations are imported, which brings its own costs and challenges to the country. So there's definitely, we see, given our location and the wind resource on our doorstep, that wind and maybe increasingly as well some amount of solar is very much part of the future kind of direction of energy production in Ireland, north and south. And as well, I'll mention as well our largest system in feed on the system. So this is the largest kind of contingency or reference event that we plan for would be about 500 megawatts. So again, it's quite large in proportion to the size of our system. And just to give a flavour of where we are in terms of energy production over the course of a year. So this is in 2020. We had a target that by 2020 we would have achieved 40% renewable electricity production on the system, and we got up to 42.5%. Most of that renewables, as I mentioned, coming from wind, with a small amount of solar and hydro and some other sources. So really, we see that wedge, that green wedge of wind, is something that is going to continue to expand and grow into the future, and the balance then predominantly from gas-fired generation on the system. Okay, so that's the introduction. The next section is about our journey to 75% non-synchronous renewable generation levels. And I suppose this journey started back over a decade ago, back in 2008. The governments north and south and the TSOs north and south worked on a series of reports, both from an economic point of view and a technical point of view, looking at what direction we wanted to go in terms of the integration of renewables onto the system. And by 2011, as the TSOs, EirGrid and SONI, we established what we call our DS3 program. DS3 was about delivering a secure, sustainable electricity system, and it had a number of different aspects to it, from the development of system capability, system tools, and our system policies that we set out plans for how we were going to develop the operation of the power system into the future. So what those early technical studies that we did back in 2011 was identify the technical challenges associated with introducing non-synchronous generation onto the power system. So as we know, power systems have always operated with large synchronous generators on them, and we were going to be transitioning to connection of lots of wind, which is a non-synchronous source of generation, which is different technical characteristics, different controllability characteristics and forecastability characteristics. So through technical analysis, we kind of developed this concept of the system non-synchronous penetration limit or metric, which is you can see in the calculation box here. So SNSP is essentially the ratio of non-synchronous sources of generation, so wind plus solar plus our HVDC imports. So all the production of energy coming from non-synchronous sources as a proportion of the demand on the system plus HVDC exports. So we developed this metric as something relevant to us as a island as a synchronous system that was kind of seemed to capture some of the technical characteristics and also as a useful metric to talk to industry and talk to stakeholders about the challenges ahead and the progress that we were making against those. So the graph kind of illustrates that kind of the proportion of our basically demand that could be met by wind, and our view back in 2011 when we were operating at an SNSP of about 50%, that we could, through development of new capability and tools and new standards, we could get up to a level of 75% SNSP based on the capabilities and technologies that we foresaw as being available at that time, but that beyond 75% wasn't kind of going to be a safe area to operate until kind of technologies and capabilities had developed further. So this was the goal we set ourselves back in 2011, to get from an SNSP of 50% up to 75% within the decade. So I kind of mentioned some of the key technical challenges that we had along the way, and I call out three here, which I'll talk through. And probably the first one was probably the key one, increasing the rate of change of frequency standard for the system. So historically, in our grid codes, we had a standard that the rate of change of frequency on the system could be up to plus or minus 0.5 hertz per second. But when we did our analysis of the impact of integrating more non-synchronous wind onto the system, which was displacing conventional generation, the system was going to get lighter, a lower inertia. And as a result, in contingency events, when we lose something like the largest system in feed, there would be a high rate of change of frequency when that happened. That would push us above the existing standard as it was at that time of 0.5 hertz. And we set a target that we would aim to change that standard up to 1 hertz per second. So this was quite a significant challenge to us, because there's probably two parts to it: the ability of the existing conventional synchronous generation on the system to be able to comply with that increased standard. There was concerns from the conventional generation back to what the generators themselves were designed to withstand. So a lot of work was done with the generators and the original manufacturers of the generators to study, that they could safely operate at this higher potential RoCoF on the system. So a lot of analysis was done by all the the generators on the system. We then tested all the generators on the system with frequency injection testing to determine that they could operate up to this 1 hertz value. So that to do all the generators, all the large generators on the system, and do that analysis and testing work took many years. And the other aspect to the RoCoF change was around the RoCoF was used as, and still is used as, a protection, anti-islanding protection on the distribution network. So with working with the distribution system operators, we had to, or they on our behalf, kind of had to make lots of protection setting changes to devices on the distribution network. And again, that took, given the sheer volume of work that needed to be done there, that took many years. But we're close to kind of, we have been trialing operation now for the past couple of years at 1 hertz per second operation, and we're hoping that by the end of this year we will have kind of completed that work and have 1 hertz per second as our enduring policy. So the other two then, the next one is around scarcity of system services. So as we displaced conventional generation on the system that provided the traditional services that the system needs, like frequency response, inertia, ramping, we needed to source those services from other service providers, like in some cases from wind, but we still required a minimum amount of conventional synchronous generation on the system to provide some of the services that we need. And then the third point is around, I suppose, more kind of thermal constraints on the system. Most of the wind that connected to the system is connected onshore on the west coast of the island, facing the Atlantic, where the wind resource is the best. But most of our demand on the system, or the large demand centers on the system, are on the east coast. So the system was never developed, the transmission system itself was never developed to transfer that power from west to east. So we still have sometimes significant levels of constraint on the system pending its reinforcement. So that was some of the technical challenges, and I suppose to overcome some of those challenges, we identified the need to develop what we call system services. So the services that we historically got from conventional generation, that we started to become scarce as the conventional generation was taken off, and we needed to find alternative sources of that, and also develop some new services that you can see here. So back in 2015, this kind of illustrates I suppose the relative magnitude of payments to largely generators on the system back in 2015. So they were getting, a generator was getting most of its revenue through the energy payment for its energy. We also had have a capacity mechanism in place, and really what were called ancillary services, so frequency response, reactive power services, was only quite a small proportion of the overall income for generators at that time. So it was 60 million euro across 7 services. So what we identified, in order to get the capability we needed on the system, and to encourage the technology development and other sources of services, we, with the regulatory authorities on the island, north and south, we developed new what we call system services arrangements. So no longer considering them ancillary, but more core to the operation of secure operation of the system, and we called them system services. So we developed 7 new system services, which I'll talk a bit more about in a minute. And importantly, we also kind of put forward the justification and got approval of a huge increase in the budget, that we were paying for those services to incentivize their delivery and development into the future. So that 60 million budget went up to what's currently an annual cap of 235 million that we pay for 14 services. So a bit more on the services and some of the new services. I suppose traditionally what were the old ancillary services were the traditional sort of reserve services like primary operating reserve, secondary, tertiary, replacement reserve, as well as steady state reactive power production. So they were kind of our original 7 services, and the new services then that we developed, well, on the kind of frequency type of services, we introduced a service called Synchronous Inertial Response, SIR, and also a fast frequency response service. So these were expecting faster outputs from the service providers than the traditional primary operating reserve, which kicked in from about 5 seconds. And just looking at our fast frequency response service a bit more, it is fast in that it incentivizes response down to 150 milliseconds, and importantly as well, we're also getting that service from a wider range of sources than we traditionally got the system, the other types of reserve from. So we get fast frequency response from demand, from wind, conventional generation, a lot of batteries on the system now as well, the HVDC interconnectors as well. So a broader portfolio of service providers in providing those services. In the longer term time frame, we also developed our ramping margin products. So ramping margin 1, 3, and 8. That equates to 1 hour, 3 hour, and 8 hour ramping capability. So this was to assist us in managing what I showed in one of the first slides, that kind of large ramp, either ramp down or ramp up in wind, that we could match that with response in other generally conventional generation that was able to kind of provide the balance to that swing in wind, and also some of the uncertainty associated with the forecast of wind. So there are some other services that we have kind of proposed or developed, but are not actually kind of not actively procuring them at the minute, but they're to do with very fast transient post-fault response of units on the system. And what this table just lists out the 14 services that we have in system services we have in place today, and a short description of what they are, just for reference. And I suppose what we're highlighting here is that we're getting a lot of these services from wind itself, from fast frequency response, the reserves, the steady state reactive power capability. So it's important as we kind of transition to more wind and other res sources on the system, that we're able to use those resources to provide the services that the system needs. The next couple of slides are on the control center tools that we developed, and again, this goes back to 2010, and has been a key kind of focus. Was key focus of the DS3 program was the development of the control center tools and capability that we needed to be able to match this ambition that we have of introducing lots of wind onto the system. So, we would have developed extensive visibility and control functionality from our EMS system, which I'll show a bit more detail on in the next slide. Forecasting capability, of course, is critical. A dispatch tool in our EMS that's been critical to managing the real-time output of wind. Some of the stability, the analysis tools that we're using in the control room, and wide area monitoring PMU capability on the system. Recent past year and even up to date, we have 3 new control center tools that we've implemented, which I'll talk a bit more about in a second. But of course, this kind of development of control center tools is going to continue into the future. So we have we've also established a control center of the future project, which is looking at what we need in the control rooms to be able to operate the system in 2030. So just to focus on some of the tools capability that we developed. So this is a slide illustrating the visibility and controllability that we have on wind and the solar that's connecting as well. So this kind of what I've outlined here is applicable to all wind farms greater than 5 megawatts on the system. So it's wind that's both connected on the transmission, large wind farms connected on the transmission system, but also smaller wind farms connected on the distribution network. So we have, I mean, things that you might expect, like the status of the wind, the availability of the wind, its actual output, megawatts and megaVARs, its forecast availability. We have forecasts looking out 5 days at 30-minute granularity, so that gives us the visibility that we need of what's coming. And maybe critically on the controllability side, from TSO to wind farm, we have that we can send active power limit set points, so we can set a limit on the active power output of the wind, and that's important for managing both constraints, thermal constraints on the network, but also when we're operating at very high wind levels, such as the SNSP limit, to keep us at that limit that we can send set points to wind farms to curtail their output so that we don't violate those limits. So there's the active power control. There's also fairly sophisticated kind of frequency response characteristics that we can set remotely. So we can turn frequency response on and off. We can also change the frequency sensitivity deadband on wind farms. So they can have a wide frequency deadband or a narrow frequency deadband to make them more sensitive. And this is all part of using the capability that's in wind to help us manage the secure operation of the power system as it displaces the conventional generation that traditionally provided this type of capability. And we can also control the reactive power of the wind farms as well. And another important tool that we have is our phaser monitoring capability across the network, or our wide area monitoring capability that we have. So we have a fairly extensive network of phaser monitoring units around the country, sort of located where generators or large wind farms are around the system. And this feeds back to a real-time sort of visualization tool in the control rooms that gives us, and I suppose this is primarily used for helping us to monitor any type of low frequency oscillation on the system. So this real-time feed from about 50 locations around the country can help us identify if there's a particular unit on the system that is oscillating, it will tell us the frequency of that oscillation, the magnitude of that oscillation, and it'll provide the operator in the control room with kind of information on how to address that. We have had some experience of very low frequency oscillations, and this has been very useful at pinpointing what the drivers of those are, and in helping the control room react to damp those oscillations. And the other kind of important part of this tool is the very high quality, high frequency, high sample data that it records. So for events on the system, such as a transmission system fault, we have lots of very high resolution information that we can use to analyze the performance of the system, and also which helps us to validate our dynamic models of generators and wind farms on the system, so we can compare what our model forecast would happen in a fault with what actually happened, and that can help is very useful in validation of models. Other new control center tools that I mentioned earlier is and I kind of just maybe highlight some of these, the first two. So our look ahead security assessment tool, LSAT. So this is kind of what we might term is the radar for the control room operators. So it gives both it does, firstly to say, it does full dynamic transient frequency and voltage analysis of about, I think it's about 800 contingencies that we model running every 5 minutes, and provides the control room with kind of a clear kind of status of, is the system secure? Have we an issue that we need to address in real time, based on real time system conditions? And importantly, we've just added functionality to this tool, which makes it look forward now up to 8 hours at the minute. So we get our demand wind forecast into the future, our expected schedule of generation on the system, the representation of the transmission system itself, the next 8 hours, and we for every hour snapshot of that 8 hours, we perform again that full transient frequency and voltage analysis. So this gives the operator kind of a look ahead capability, and that a potential problem might be coming down the line, and gives them time to react and address that. Another tool we've just recently introduced is our ramping margin tool, and this is aimed at helping us in the scenario that I spoke about at the beginning. So that kind of large ramp down in wind production. So it has awareness of how the wind forecast is expected to change in the future, and it will ensure that we have enough of the ramping capability over 1, 3, and 8 hours to be able to match that kind of forecast ramp, but also to deal with some of the uncertainty that is always going to be around any form of wind forecast. So this is really important tool to us in being able to deal with those type of events. And thirdly, we have a new tool that's in the process of being introduced into control rooms over the next couple of months, called our voltage trajectory tool, which is designed to give us kind of, again, that forward-looking plan to manage reactive power resources in the network, and ensure we can keep voltages within limits. So that's kind of the technical, the market, the services, the tools side of things. And I suppose the one thing we kind of identified earlier in the DS3 program that we established was the necessity to engage with industry in this whole process. So it wasn't that the TSOs were going to do all of this on their own. We needed to engage with the wind farm developers, the conventional generators who, for example, had to adapt to a new RoCoF standard. We had to get funding, and we needed the regulatory authorities to fund the payment of services. We engaged with academia, other equipment manufacturers, our neighbours in Great Britain, National Grid, kind of sat around the table with us as well to get their insight into what we were doing, and the distribution system operators north and south were at the table as well, again linked to the RoCoF kind of work that they needed to do. So this was really important way to communicate with industry what was happening, and get industry buy-in to what we were doing. through the establishment of this what we called our advisory council, which is effectively still going since 2011. So next couple of slides are on where we are today. So where we're operating today. So we have kind of established this upper limit of 75% on the SNSP metric. So we have hit that. We hit that last year. We've hit it this year as well. The illustration here shows kind of how that SNSP metric evolved over the years. It's been, you know, it does take time. There were certain capabilities, tools that we needed to be in place before making each step on this SNSP change. We also, each change that we make, we trial it for a period, we observe how the system performs, and we do analysis to validate that that the system is still secure as we make each step. So we're at 75% now. And just by way of an example, this is a snapshot of a day back on the 11th of June. So in our summer, and it was quite a high wind day. A day when we were up at. You can see the red dotted line here is the SNSP. So it's on this axis, on the SNSP axis. So that was up at sort of above 50% all of the day. It's sort of, I think it was averaged about 65% for the day and peaked at 75%. So that was a very high wind day for us. And just to compare it, I sometimes when we talk about SNSP, the importance of the interconnector imports and exports are important in the calculation, because if you just look at, say, the percentage of wind and solar as a percentage of demand, we were actually up at 88% on that day, and we have been at higher levels than that. But for our SNSP metric, we factor in the imports and exports. So one other thing to note in this still is, you know, you can see that with the green line, so the yellow line is our system demand on the day. It was a summer day, so it's a relatively flat profile. The green then was the wind and solar actual production, and the green dotted is the wind and solar availability in that day. So you can see that there was still more wind generation available, but because we were close to this or up at this SNSP limit, and maybe there were other constraints on the system, the wind was constrained or curtailed down to below its actual availability, and obviously and below the actual demand of the system on that day. Okay, so that's kind of how where we are today. You know, not uncommon for us to get up to 75% SNSP levels. So now that represented, I suppose, the kind of the aim of the DS3 program that we kicked off in 2011. And so I just want to finish maybe with one slide which talks about kind of the next phase of work that we're looking at. So you might remember at the beginning we had achieved this 40% RESI target in 2020. So RESI is the renewable energy sources producing electricity. So that's the sort of across a year that 40% of our electricity production came from renewable sources in 2020. We slightly exceeded that. But the target now is set by governments north and south, is that we are aiming to achieve 80% RESI by 2030. So what that means from our point of view, from an operational point of view, to achieve that 80%. So we're operating today at 40% RESI. with an SNSP, so the instantaneous penetration of res of up to 75% to get the average of 40% across the year. So to get to 80% resi on average, of our energy across the year, we actually need to get SNSP up to 95% or higher by 2030. So that's kind of our current plan. And we've produced a plan that we published last year called Shaping Our Electricity Future. And that brings together kind of there's the operational kind of aspect of this, which I've kind of focused on in this presentation, but there's also the network development, the connection of the renewables, not just wind, not just onshore wind, but there's big plans for offshore wind. There's big plans for lots of solar to connect as well. So the network development to accommodate that, new market arrangements, and kind of engagement with industry. So there's a new program called Shaping Our Electricity Future is I suppose coming in now, replacing what was the DS3 program that got us to the 2020 targets. Yeah, so I think I'm just about on time there. That's the end of that. So I hope people found that useful, and we'll see if there's any questions now. Charlie?
Okay, thanks, Simon. That was quite a whirlwind tour through the last 8 years. I have to ask, after listening to that and thinking about all the things that you're doing, what does the next 8 years look like for you? Just this next phase. I mean, are you feeling good about it? Are you feeling concerned? What's the feeling there about the ability to get to that 80% res and 95% SNSP?
Yeah, I think the feeling is maybe we've the hardest bit is yet to come. I think we've built a very good foundation for where we are today, but I suppose the volume of renewables that needs to be connect to hit this target over the to the end of the decade is more than we have on the system today. So there's the physical connection of the renewable energy sources, the development of the grid itself, or it's going to be quite a project to do all that work, and kind of the operational challenges I think are going to push us even more to be able to get up to 95% SNSP. Now we think we can do it. I mean, we are doing studies, and I suppose that was the basis of the original program, was do the analysis to show what you need to be able to get to the target. So that analysis is progressing. I suppose some of the things that might help us along the way is, for example, we've just kicked off a process to procure synchronous condensers that will help us provide inertia, short circuit contribution, reactive power on the system that will hopefully allow us to be able to take off some of the conventional generation that's on at the minute to provide those types of services.
So you've come a long ways, and you've still got a long ways to go. But
absolutely, yeah.
Good answer.
Yeah.
So I'm going to move to the Slido questions here. We've got a lot of questions. I'd like to get through as many of them as we can. First one here is, do you have any tool used in the control room for system strength monitoring?
No, not well. We monitor, I suppose, fault levels on the system from a point of view of making sure that we stay within equipment ratings where there are high fault level areas on the system. So we have that that is in our EMS system, but we're not, I suppose what the question is probably thinking of is more for low short circuit, low fault levels on the system, what are the issues that might bring. And certainly that's something we're in this next phase of work that we're going to be very focused on. We don't have metrics or tools yet that help us with that, but it's on our radar to develop those metrics and to the tools that we need into the future, because we think that's going to be a very important kind of aspect of system operation in the future, is as you know, as we integrate more non-synchronous generation and the conventional generation kind of reduces.
Yeah. Okay, thanks for that. The next one I'm going to ask is, does the slide showing November 11th, I think that was very early in the presentation, indicate curtailment to avoid exceeding 75%? And how much curtailment does EirGrid experience? I know a lot of people measure the percent of energy curtailed on an annual basis or some other such measure.
Yeah, so I think in this particular day there still would have been some wind curtailment and maybe constraints. So I suppose our definition of we kind of distinguish we define a constraint as something that's network limited. So it's a thermal rating on a line drives constraints in our terminology. Curtailment is more, from our point of view, driven by the operational limits like SNSP or min inertia on the island. So yeah, curtailment levels, I suppose we probably are, constraints are roughly I think about 5-6%, and curtailment is similar, 5 or 6%. I think that was from last year. Or so in total, I suppose the dispatch down for constraints and curtailment is, you know, is something that's been high recently, of maybe just over 10%, 10 to 12% in total. And you know, it's something that I suppose that's what's really driving our push to, you know, to be able to evolve the constraints we have on the system, like be able to raise an SNSP, be able to reduce the number of synchronous generators that we have on the system.
Yeah, I think that's a common experience with a lot of people pushing high levels of wind and solar on the system today. Okay, next one. The increased cost to provide the new services such as inertia, reactive power, etc., is it able to be made up from the savings of less import of fuels?
Yeah, I'll just go to that slide. Yeah, so I mean the increase in the budget that we got for the payment for these services, absolutely. I mean, when we put forward the case, you know, we as the TSOs kind of developed the case for the technical these are the technical services that we need on the system. To incentivize that capability, we're going to need to pay, you know, for that to be delivered. So we would have developed kind of the case for this and presented it to our regulatory authorities, north and south, you know, to get the benefits of introducing wind and being able to then reduce the energy costs of the system, because we weren't maybe importing as much fossil fuels from overseas onto the system, that we were going to get savings from that. So yeah, I mean that would have gone through a fairly rigorous process with the approval of the regulatory authorities, north and south.
Okay, question on pumped hydro. Do you have any, and what are the challenges associated with it in Ireland?
We have a single 270 megawatt pumped hydro station. It it was developed back in the probably early 80s, but really we don't proportionally, probably not proportionally not that significant in terms of meeting the future challenges of energy storage. Yeah.
Okay. Question on capacity market. There was another question about capacity also. I'll just kind of combine them here. Do you have a capacity market for keeping enough installed capacity available? Can you share a rough figure about the yearly cost of capacity payments? And there was a related question about how much other capacity do you have on the system?
Yeah. Yeah, I mean, there's a total of about, I think it's 10 gigawatts of capacity on the system. We do have a capacity mechanism on the system today. I I don't know how much what the expenditure on that is. So yeah, I can, if somebody wants to leave a contact details, I can get back with a bit more detail on the capacity mechanism that's in place. And even if you kind of, if you could search for it, there would be publicly available information on that. But if somebody wants to make contact directly, we can get back to them with the answer.
Okay. Question on forecasting. What kind of forecasting systems do you use, and what is the current accuracy? And would improved forecasting accuracy help in any way to achieve the 80% res goal by 2030?
Yeah, so I'm presuming this is forecasting around renewable,
Yeah, let's say wind and,
wind. Yeah.
wind and solar. Yeah.
So our approach is that we source forecasts from two external vendors. They provide us with a 5-day forecast at half-hour granularity for essentially for each wind farm on the island. So we provide them with the location, the capacity of each wind farm, and they provide us with that forecast at essentially wind farm granularity for the next 5 days. So how accurate is that? Is a good question. I suppose one of the things that we've developed, the ramping margin tool, so that with the forecast, we also get the uncertainty associated with the forecast. So there's a central, based on all the models that the wind forecast vendors run, they have a range of high and low kind of forecasts about a central median, and so we get the range of forecasts, and we use that uncertainty in our ramping margin tool, so that while we will schedule to a central kind of forecast, but we will also build in the uncertainty associated with the forecast and ensure that we schedule enough kind of ramping or replacement capacity if the forecast is, for example, short of the central forecast. But it's very hard to sort of quote statistics on accuracy, because it depends so much how it's actually measured and in what time frame it's measured. I think there's probably information again available on our website about some of the statistics around that. It can be quite, it can be out by over 1,000 megawatts at times, if there's a big ramp event on the system, and that ramp happens maybe an hour later than what we expected, like on that day that I showed at the beginning. If that ramp had ramped down, had it started maybe an hour earlier, you could be talking about 1,000 megawatts or so or more of a difference.
Sure.
Yeah.
Okay, we're getting near the top of the hour, so let me take one last question. Simon, I'm going to skip a little bit here because we haven't spoken about this topic yet, but where do grid forming resources fit into your plan to get to greater than 90% SNSP? Will there be requirements or demonstrations, and do you see any value here?
Yeah, I think like grid forming is a very hot topic at the minute. We don't have any on the system at the minute, but we do expect as part of our plan for the next number of years that grid forming will be considered as part of that. You know, we intend to develop models and do studies, and hopefully we will be trialing the technology on the system at some point. So we have a process whereby we kind of invite trials of new technology onto the system to learn from it. But I think we're probably in the learning stage still at the minute, I would say, on grid forming. But you know, we do anticipate it playing a role into the future.
Stay tuned. Okay, we're just a little past the top of the hour, so we're going to need to wrap it up. Simon, thank you for taking us along with you on that fascinating journey. I know you're not at the end of the road yet, but you're certainly one of the furthest along. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll get the responses to your unanswered questions posted as quickly as possible. There were a lot of them, so it was a very engaging webinar. We appreciate everyone's engagement, and if you'd like to stay engaged, I'd invite you to participate in the next ESIG webinar on November 28th on interregional transmission targets in Europe with Peter Markusen of EnergyNet, the Danish TSO. Interregional transmission is a big topic here in the US as well. And further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Simon, I want to thank you again for this very fascinating webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.
Thanks, Charlie. Thanks, everyone. Bye.
Thank you.